I thank you all for watching my videos. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We will now discuss the solution of a problem from the question paper CSIR National Eligibility Test held in the month of July 2024. This question is from the section Analysis, and the question is related to surjective, injective and continuity of functions. This question is from the part C, which is a multiple select question. There can be more than one answer and it carries 4.75 marks. The question ID is 704070. This question is also suitable for all these examinations. Right. The given question is, let K be a non-empty subset of the set of real numbers and F be a continuous function from K to K such that mod of x minus y less than or equal to mod of fx minus fy for all xy belongs to K. You have to remember this. Right. Which of the following statements are true? We are given 4 options. Option 1, f need not be surjective, means is not onto. Option 2, f must be surjective if k is the closed interval 0, 1. Option 3, f is injective. Injective means 1 to 1, and f inverse from f of k to k is continuous. F is injective and f inverse defined from f of k to k is continuous. Option 4, f is injective but f inverse defined from f of k to k need not be continuous. So between these 3 and 4, one of them must be true. The other, if one is true, the other will be false. Right. We will now discuss the solution of the problem in detail. We are given a non-empty subset K of real numbers. Given f is a continuous map from K to K, satisfying modulus of x minus y less than or equal to mod of fx minus fy for all xy belongs to K. So, we first claim that such a function f is injective, that is f is 1 to 1. We will show this. Now, f of x is equal to f of y will imply mod of x minus y less than or equal to mod of fx minus fy, and fx is equal to fy, then mod of x minus y is less than or equal to 0, because fx is equal to fy makes fx minus fy to be 0. So thus we get modulus of x minus y less than or equal to 0. Agreed. Agreed. But the modulus function is always non-negative. That means to say modulus of x minus y is greater than or equal to 0. That means this implies 0 less than or equal to modulus of x minus y less than or equal to 0. So that will imply modulus of x minus y is 0. This implies mod of x minus y is equal to 0 if and only if x minus y is equal to 0. X minus y is equal to 0 will imply x is equal to y. Thus, whenever f of x is equal to f of y, we get x is equal to y. This shows that f is 1 to 1, that is f is injective. This is required for us while we discuss the solutions of the options. Right. We move to the next slide for the discussion of option 1. Option 1. F need not be surjective. Is it so? Is it so? So, is not surjective means with these conditions, we have to provide an example where surjectivity is lost. So, look for such a kind of an example. So, let K is the semi-closed interval 1 to infinity and F be a map from 1 to infinity to 1 to infinity be defined by f of x is equal to x square plus 1. Is trivially, f of x is equal to x square plus 1 is always continuous. So clearly f is continuous and we want mod of f of x minus f of y. So that will be equal to mod of f of x square plus 1 minus f of y is y square minus 1. And that will be 1 and minus 1 cancels and you will get 1 modulus of x square minus y square. Agreed. Now factorize. Factorize modulus of x minus y into modulus of x plus y. That is the factorization of x square minus y square. Agreed. Now xy belongs to the semi-closed interval 1 to infinity. That means x greater than or equal to 1, y greater than or equal to 1. Then thereby x plus y is greater than or equal to 2. 1 plus 1, 2. So this will imply 2 times modulus of x minus y because xy belongs to the semi-closed interval 1 to infinity. And 2 times mod of x minus y is greater than or equal to mod of x minus y. So thus we get mod of f of x minus f of y is greater than or equal to mod of x minus y for all xy belongs to the semi-closed interval 1 to infinity. Thus f has those characters. That is f is continuous and f satisfies the given condition. Right. He is a candidate for us. So is he surjective? That is the question. That is the question. We look for the pre-image of 1. This is, observe that 1 belongs to the semi-closed interval 1 to infinity in the codomain and this has no pre-image in the domain. How do we say? For if there is a pre-image, say x belongs to the semi-closed interval 1 to infinity which is the domain such that f of x is equal to 1. That implies x square plus 1 is equal to 1. That implies x is equal to 0. Is 0 an element of 1 to infinity? No. So that means if at all this happens, x must be 0. Therefore, but 0 does not belong to the semi-closed interval 1 to infinity. We get a contradiction. So this contradiction shows it has no pre-image. Thus, it is not onto, that is not surjective. So, option 1 is true. Option 1 is true. Right. We move on to the next slide for the discussion of option 2. Option 2 says f must be surjective if k is equal to 0 to 1. So, if you restrict, now if you take k to be closed interval 0 to 1, then f is surjective. When f is continuous k to k and f satisfies that condition. So we have k is the closed interval 0 to 1, f a map from k to k is continuous, is all hypothesis and satisfies this condition. Agreed. Agreed. And we will prove that it is surjective. Right. So now we take x is equal to 1, y is equal to 0 in this. Then this will be mod of 1 minus 0 is less than or equal to mod of f of 1 minus f of 0. Agreed. That means 1 less than or equal to mod of f of 1 minus f of 0. But where this f of 0 will be? F is k to k. So f of 0 belongs to k and f of 1 belongs to k. K means the closed interval 0 to 1. So f of 0 belongs to 0 to 1, closed interval, f of 1 belongs to closed interval 0 to 1. Then what will be f of 1 minus f of 0? It will be less than or equal to 1. So this will be 1 less than or equal to mod of f of 1 minus f of 0 is less than or equal to 1. Why it is less than or equal to 1? Because f of 1, f of 0 belongs to the closed interval 0 to 1. Their difference is less than or equal to 1. So that means it is a sandwiching. So this will imply mod of f of 1 minus f of 0 is 1. That much I can say. That much I can say. But what is f? F is injective. We have already seen. We have already seen that f is injective. Then we recall a theorem from the analysis. A continuous function defined on a closed interval. Yes, this is closed interval. This is continuous. This is continuous. It is also injective. It is injective if and only if it is strictly monotone. So f is injective, f is continuous, f is continuous defined on the closed interval, and it is injective. So by this theorem, f is injective. F is an injective continuous function on the closed interval k is equal to the closed interval 0 to 1. Therefore, by this result, f is strictly monotone. Strictly monotone means it may be strictly increasing or strictly decreasing. Let us consider first, suppose that f is strictly increasing function. Now, 1 greater than 0 will imply f of 1 greater than f of 0 because f is strictly increasing, and thereby f of 1 minus f of 0 is greater than 0. Go back to this. So modulus of f of 1 minus f of 0 is equal to 1 will imply modulus will go away because f of 1 minus f of 0 is greater than 0. So f of 1 minus f of 0 is equal to 1. And f is strictly increasing. F is strictly increasing. F of 1 minus f of 0 is equal to 1 will tell you f of 0 is 0 and f of 1 is 1. Thus the range of f, so f is mapping everything from 0 to 1. So that means the range of f is k, the closed interval 0 to 1. Thus the range is equal to codomain. Therefore, it is surjective. That is onto. So in this case, when f is strictly increasing, f is surjective. So let's move to the next slide for the discussion of the other possibility. That is, suppose f is a strictly decreasing function. Now 0 less than 1 will imply f of 0 greater than f of 1. Why? Because strictly decreasing, and that will be f of 1 minus f of 0 will be negative. And go back to this. When it is negative, mod of that is minus of f of 1 minus f of 0. So mod of f of 1 minus f of 0 is 1 will imply minus of f of 1 minus f of 0 is 1 because f of 1 minus f of 0 is negative. That means f of 0 minus f of 1 is 1, and it is strictly decreasing. So that means f of 0 is 1, then f of 1 is 0. Then it is decreasing. That is why f of 0 is 1 and f of 1 is 0. So the range of f is the complete k, that is the closed interval 0 to 1, and f is surjective because this range is coinciding with the codomain of f. So f is surjective. So in any case, f is surjective if k is the closed interval 0 to 1. In general, it is not. That is option 1 says. So in option 2, when k is the closed interval 0 to 1, f is surjective. Thus, option 2 is true. Right. We move on to the next slide. for the discussion of option 3. Option 3 says f is injective and f inverse from f of k to k is continuous. And in this, f is injective we have already proved. And I will call option 4 also. Option 4, f is injective but f inverse f of k to k need not be continuous. So between these 3 and 4, one will be true, the other will be false. Right. We have already shown that f is injective. We have already seen that f is injective. Now, from f of k to k, this function f, that means we are f, will the function, will there be f inverse from f of k to k? So let's see that. We have f of k, that is the image of k under f is the set of all f of x, x belongs to k. So where this f of x will lie? F of x will lie in k. So that means f of k, capital K, is contained in k. Agreed. Agreed. F of k is contained in k. Now f from k to f of k is surjective. Yes, it is surjective because we are restricting the codomain to be f of k, not k. We are restricting to f of k. So for each element of f of k, we have pre-image. So therefore it is surjective. Surjective. F k to f of k. It's surjective. But f is injective. Injective. From k to k is injective. Therefore k to f of k is also injective. So f is injective and surjective. Therefore f is from k to f of k is bijective. Therefore its inverse exists. The inverse will be f of k to k. So f inverse from f of k to k exists. So now we have to show that it is continuous. So required to prove that f inverse from f of k to k is continuous. Right. So now let x and y be any two arbitrarily chosen elements of f of k. So they are elements of f of k means x is equal to f of a for some a belongs to k and y is equal to f of b for some b belongs to k. Agreed. This will imply a will be f inverse x. Yes, f inverse has a meaning. So b will be f inverse of y and ab are elements of k. So f inverse x, f inverse y belongs to k. So we have got them. Take them, they are the elements of k. Go back to option 1. So mod of f inverse x minus f inverse y, they are the elements of k, is less than or equal to mod of f inverse of x minus f of f inverse y. We are using 1. Agreed. F of f inverse x is x, f of f inverse y is y. So this is mod of f inverse x minus f inverse y is less than or equal to mod of x minus y for all x y belongs to f of k. Right? So this is what we got. And if you look at this carefully, this is something to do with the Lipschitz function. So let's recall the definition of the Lipschitz function. A function f from the domain D to R, where D is a subset of R or R power n, is said to satisfy Lipschitz condition if there exists a constant capital L such that for all x1, x2 belongs to the domain D, mod of f of x1 minus f of x2 is less than or equal to L times mod of x1 minus x2. The constant L is called Lipschitz constant, and if such an L exists, f is called the Lipschitz function. And a property of the Lipschitz function is every Lipschitz function is uniformly continuous. Look at this one. This is true for all xy belongs to f of k. So as per this, f inverse is a Lipschitz function. F inverse satisfies Lipschitz condition. In other words, F inverse is a Lipschitz function. Here L is 1. Here L is 1. So recall, now look at the property. So when it satisfies the Lipschitz condition, it will be uniformly continuous. F inverse is uniformly continuous. When it is uniformly continuous, F inverse is continuous. So thus we got F is injective, and F inverse defined from f of k to k is also continuous. We have shown you. So thus option 3 is true and option 4 is not true. Option 4 is not true. So what is the answer? The answer to this question is options 1, 2 and 3. Option 4 is not true. So that is the detailed discussion of the solution of the given problem from the real analysis, which is related to the surjectivity, injectivity and the continuity of functions in the given context given in the question. Right. And it is definitely not that easy question. It is definitely a difficult question. I am sure that you have understood the solution of this problem. I thank you all for watching this video. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. We hope to meet once again in another episode of learning. I wish you all the best. Thank you.